Alright, this is a picture I was hoping was in the PowerPoint, and it wasn't. But when you're getting your tester, say this is at the disconnect. So you have a disconnect where your equipment's at. So you always check on the line side to make sure it's hot. Okay? Line to line, line to line. So here they're doing it A to B, and then they're doing it from B to C. Then they're going from A to C. Okay, so you get your tester, and you go, and you're measuring across. So you should get the same voltage here as here and here. Okay, you should get the same voltage. If you don't have the same voltage, and then something's wrong in your supply, so coming out of the panel or distribution, there's where the problem may lie. So your voltage should be the same. So this is a 480 volt circuit. I should have 480 here, 480 here, 480 here. Everything's okay. If I don't have that, and then the problem is at the supply. Okay? And then over here, what they're doing is they're checking the individual. Once I establish that my voltage, my input voltage is correct. Once I establish my input voltage is correct, I can go back and check the individual fuses. Okay, so I went from A to B, I should have 480. A to C, I should have 480. And then I went from A to B, because I haven't tested across A. And then I went from A to B, reversed it. I went to the bottom part. Okay, if I'm picking up 480 on each one, and that means that all my three circuits, all my three fuses are good. If it doesn't, and then one of those fuses is bad. So let's say I measure A to B, top hot to switch leg, or whatever you want to call it. So this is my line side end, this is my load side. So I'm going from my line side to my load side. If I got 480 volts in my meter, that means this fuse is good. I come over here from A to C. If my voltmeter is reading 480, and then C fuse is good, all of a sudden I go to A, and I go from A load side to B line side, all of a sudden I get 0. Well, that means that my A fuse is bad. That meant that my fuse on A is bad. Okay, so this is how you can test. Yesterday I said that I would go from a ground, so the metal frame, go back here, oops, got the mouse over here. This is your textbook, so I have this one here. So the other thing I can do is I can find the ground screw, go to hot, hot, hot. So if I establish these are all hot, let's say I got a 240 480. I got a 240 480. So I'll go from here to here, I got 240, I go to here, I got 240, I go to here, I got 240. Guess what? When I come down here to the bottom, I should get the same thing. If I don't, then one of those fuses may be bad. Okay? Or it's a 120 240 or 120 208. Whatever the voltage may be. Okay, let's say 120 208, it's 3-phase Y. So we don't have to worry about that high leg on the B and get anybody confused there. So I go from here to hot, to hot, to hot. I got 120 volts on all three. 120, 120, 120. Okay, then I come back and I go from hot to here, and I got 0, 120, 120. That means that my fuse on A is bad. Okay, this is a textbook. Luckily I got it online. The company was real good to me. So this is how we're troubleshooting. How you can troubleshoot a disconnect. I guess it's not on here. I keep trying to go to over there. The book's a little bit different, but yeah, well, I got this here. We'll go to the PowerPoint. They're talking about control circuits. The one I was looking at was a different page further down. Here, let me go to the next page. There it is, where they're going to the line side. So now they're checking on the line side. Okay, so you can do it. You can do it at the lugs, or you can do it at the individual fuses. It's up to you. Sometimes you have a cover that goes over this, so you can't see the fuse, but you can get to the lugs. Sometimes you can't get to the lugs, and you have to take that cover off. All right, let me go back here. I'll go back to it as I need. If I need it, if there's a picture that I know of that we need to cover, I'll just go back to it since I have the actual thing. Alright. It says troubleshooting a control circuit. Okay, step 1. Check to see if you got voltage at the transformer. So, or if you have your control circuit, if it's coming off a breaker somewhere. So it says a control circuit may be the source of the trouble. Follow the steps steps illustrated. Check input voltage of the control transformer. Make sure you got power coming in. Make sure you got power going out. Because there's sometimes you'll have a fuse on the transformer for your input, and you'll also have a fuse on your secondary side of the transformer going out for the control circuit. So that way it's protected on both sides. Why? If I got a 50 excuse me, a 50 VA transformer, a 50 watt transformer, for all it's doing is the controls, the stop starts. Let me see if I got a picture here for that. Okay, there it is. I do have it on here. So there's a fuse on the primary side. There's a fuse on the secondary side. Why? This is a 50 watt transformer because all it's got to do is run the stop starts. It's got a little light over here. So all it's got to do is take care of that. Then you don't need a big transformer. But you still got a 20 amp breaker. Or it's coming off the hot side of the motor. And the breaker is a 50 amp breaker, or whatever it may be. So you have to protect this transformer so it doesn't create a fault. If there's a fault, it blows the fuse and it doesn't go back and cause other problems. So we have a primary protection and we have our secondary protection. So you want to make sure you can check your primary voltage coming in and your secondary voltage going out. Okay, so you want to test. Step 1. Okay, check your input voltage. Step 2, check your output voltage. Okay, now they're going to step 3. This says verify the current drawn by the circuit. So in order to, if your circuit's working, there is going to be some current because you have the coil inside of here is going to draw current. Switches, the switches don't draw any current, but the coil does, and it's minimal. But you can read it. Okay, whether you got one of these, you got one of these, or one of the little ice cubes. Okay, there's a coil inside of it, so this will draw current. So you can get your amp probe, clamp it, and see if it's got current. Isolate the control circuit with a fuse jumper. If this motor starts, install the control circuit is faulty. So what they're doing is they're just getting the wire coming off the hot, off the one, so they're bypassing your stop starts and they're going straight to the controller. So again, on this one I said A1, this one is 120 volts. A1 would be my grounded wire, A2 would be my switch leg to the coil. So that would come off the 14, the 4, and the 3. So here's my auxiliary. So 13 and 14 is on my auxiliary, and then it goes to the A2. Okay, so I can bypass to make sure. If the coil closes, thing is, if I get my screwdriver or whatever I may get, push this in, and the motor turns on, then obviously I got a problem somewhere else, because power is going to it. Okay, so it might be the stop-start switches. The contactors may have blown out. The contactors on this might have gone out. Your another thing is your overload relay might have tripped and you forgot to reset it. You know, it could be one of the relays that's not closing and holding. So you have to check everywhere else. And then step 5 is the motor does not start with the jumpers installed. Check the voltage across the overloads with the jumper still in place. So here I have another, this is my overloads. So I'm going to have a wire in. So this is normally open, normally closed. So this is closing. If this is not closing, if I hit the reset, this is not closing, then this may be the problem. You know, biggest problems I used to run into is they have a 5 horsepower motor, and that motor goes bad. Okay, and then they would come in there. The engineers would come in there to change it out, and they go look on their stock. And when they looked on stock, they didn't have a 5 horsepower, but they had the same frame number and motor size, same voltage at 7.5. And all of a sudden they put the 7.5 in. And then he called me up, hey Mundo, we got a motor that doesn't stay on. We don't know what the problem is. We just changed it out. It's a brand new motor. Okay, what's causing? The overloads. Why? Because the overloads were sized for the 5 horsepower, not sized for the 7.5. Okay, so it's one thing you should look at. Same thing, you know, all of a sudden go there and you, oh, okay, right. You look at the motor, you try to make sure that you're looking at the motor, and instead of getting and replacing what's there, you try to find the size of the overloads for that motor, and then you just change them out. Okay. The other thing is always check to make sure your motor is good. Now going back to this picture. Okay, with power off, whether at the disconnect or at the breaker. Make sure you got your lockout tag. You locked it out, tagged it out, locked it out. See, that's why this one's red, emergency. Okay, so whichever one you use. Lock it out, tag it out. Now you know power's off and nobody can turn the power back up on you. And you get your amp probe, or you get your tester, your resistance tester. Say this one. I go to ohms. With ohms, what I usually do is, let me go to the next one. I like the other picture better. Oops. Doing a resistance test. Ground to here, to here, to here. Okay, so what I'm going to do is I'm going to go to ground and go to the fuse, and the fuse. Okay, yesterday one of the questions was, when you're doing resistance measurements, what don't you always do? What you should never work on an energized, what's the question? You should never do resistance measurements on an energized circuit. So always make sure it's off. And then you would go to the ground and touch each one. Guess what? If you read, anytime you go from the ground to a hot with the power off, your tester should say OL. Just like this one says OL, open line. Okay, if you start getting numbers in here between the ground and one of these hots, there's a problem. Okay, that's one thing that I didn't do, that I didn't observe. I didn't go through that step because I took somebody else's work. Okay, just referring again, now that I got a tester and I got a disconnect up here so I can show you. Always when you're testing the motor, okay, turn power off and check resistance. If a breaker trips, if your overloads trip, why did the overloads trip? They shouldn't. Why did they trip? Okay, first step is there's a problem within the windings of the motor. Is it going to ground or is it going to hot? And then you just go hot to hot, hot to hot. Again, just go A to B, A to C, and then it should get a reading, and then go from, yeah, that's it. So if you go across each phase, then you're checking across the phases. Oh yeah, C to, A to B, A to C, and then B to C. Make sure your windings are, the numbers are the same. You should pick up something when you're doing across the windings. You should pick up resistance because it's going across the windings. But if that number comes down to 0, then there's a problem. You know, if you go, so if you go from, say, A to B, and it comes down to 0.1, that means there's a dead short between both of them. So if you go to here, and it goes to 0.1, that's almost 0. That means that you got a direct short between two phases. We're talking about control circuits, not other stuff, but I just can't help myself sometimes. Alright, so control circuit. This is a control circuit. We got power coming to the transformer. Transformer goes in, stops, starts. Here's a stop, here's a start. Here's my relays, and here's my contactor. Okay, so this is my normally open. Here's my normally closed. This is where the overloads are at. So this part here is always closed. This is my overloads. That's this part right here. On the overloads, do you want it normally open? Do you want it normally closed? What are they going to be doing? You know, you may have a reverse. One is a reverse and one's a forward. So you might have them different. But one closes, the other one opens. So it allows it so you can do different things. Troubleshooting control transformer. Input voltage should be, when you're testing the transformer, when you're going across the transformer, you're testing, your voltage should be 7.5% of the rating. Should be within 7.5% of the rating. So they gave you sample problem 18.1. It says the control transformer, what step voltage down from 480 to 120 is being tested. What are the acceptable voltage readings for the input and output voltage? So 480 times 7.5% equals 36 volts. So I can lose 36 volts. So 480 coming in minus 36, that would be 444. And as long as you're in that, you're okay. Output voltage. Or the output, and then 120 is 9 volts, so I can go from 111 up to, I forgot to do it upways, so it's 36 volts up or down, within 7.5% of the rating, up or down. So it says 444 and 516. And then for the 120 volts, it's 111 to 129. Because it's 9 volts. 9 volts up, 9 volts down. Motor repair. Determine the cause of the failure. Oh, let me see. Something else here that I want. Control transformers must also be checked for grounding problems. Performing a grounding test on the control transformer can be easily done. Motors are generally the most expensive electrical equipment with the commercial and light industrial operations. Motors are dependable and require only minimum maintenance. However, they eventually fail and must be repaired or replaced. Okay, so you have to determine the cause of failure. Here it's also going, it says small defective motors are usually discarded and replaced with new ones. It costs less to replace a small motor than it does to repair. Large motors are replaced to prevent downtime, and old motors are sent to the shop for repair. The required motor can be placed in service later. Troubleshooting motors involves 2 basic operation concepts. Determine the cause of failure and reduce the chance of failure occurring again, in general. Okay, so determine the cause of failure. What causes a motor to fail? Okay, so you got an area that all of a sudden started getting hot, or somebody forgot to oil the bearings on it, so it starts to work harder. Okay, that can cause a motor. Why? Because if it has to work harder, it's going to get hotter and then cause the fail. Or you got an area at one time, motor was in there and the temperature was, say, 80-90 degrees. All of a sudden, new equipment is installed and the temperature goes up. Okay, and you have an area that's hotter than what the motor was designed for. We had that one area that happened where I worked at, and motors started to fail. And there's like, well, why are motors failing? Well, it was a 40-degree C room, and we had a room that was an average temperature of 130 degrees. Well, the temperature was too hot for the motors, and it couldn't handle the heat. So we had to change the motors out, and we had to change the wiring because the wiring was old TW wiring, so we had to pull new wires in to be able to handle the higher temperatures. In general, motors may fail for one of the following reasons: high or low voltage, unbalanced voltage or current at the source, excessive load, overheating, single phasing, excessive cycling, excessive moisture, and motor control center problems. Okay, so checking for high and low voltage at the motor source. Check your high and low, so we just did that. And then motor source should also be within 7.5% of the motor rating. This breaks it down instead of like the book. So the PowerPoint is nothing like the book. So there's talking about, you got the high voltage down here. Okay, so it gives you all the different points and then explains each one. So, but on the PowerPoint, I got one sentence. Okay, check for high and low voltage at the motor source, and it has to be within 7.5% of the motor rating. Unbalanced voltage. Unbalanced voltage or current at the power source. So what happens? Let me change my plate sheet. Oh, how do you test? How do you test for voltage? Okay. Well, this is the bottom part. But what you want to do is check the input voltage. So when you want to check, so if I got a 12208 and it's, let's say it's 118 to ground, 118 to ground, 120 to ground. Okay, it's all within limits. Why? Because we said each one can be either down to 111 up to 129, 7.5%. Okay, but if I go in there and I measure, this one is 118, this one is, let's say that one's 105, and then this one is 120, 118, 119, whatever it may be. So A and C are within the limits, but B is too low. So what happens is the motor is kind of doing this. Why? Because it's not running balanced. Because I don't have the voltage between across 3 windings, so the motor starts wobbling. It can start vibrating, can start wobbling. It can cause problems and the motor overheats. It's an excessive, it can be excessive loading. So unbalanced voltage of the current at the source and unbalanced voltage at the power source is differential to the motor windings. Unequal voltage can cause the current to be several times higher relative to the voltage imbalance in the motor and heat the motor windings. This reduces the torque, causing vibration and eventually bearings or winding damage. Voltage should be checked with a wattmeter, with a voltmeter, again, for unbalanced voltage. Go back to the PowerPoint. So, unbalanced voltage and current at the power source, guess what? Current changes. Because if I got 118 volts here and I got 105 volts here, well, the current changes. Current causes, excessive current can cause extra heat, damage the windings. Overheating. Oh, what else? They didn't have down here it has excessive load is one of the major causes of motor breakdown. When the motors have an excessive load placed on them, they try to compensate by working harder than they are designed to. The motor will draw excessive current. This excessive current causes heat, and additional heat imposed on the windings can cause the motor to fail prematurely. Okay, so you have to be careful with this excessive loads. Voltage unbalance creates more heat. It's trying to work harder, and it's like you know, if you're working calm and you're okay, you're cool and everything, and then all of a sudden you gotta put some pump into it, what happens? You start to get hot, you know, so you have to be very careful. Just like when you're working in outdoors, you have to be careful. You have to keep yourself cool so you don't overheat. Same thing with these motors. So what you want to do is, in that case, is you get your amp probe, check the current, make sure your current is balanced. Make sure that your current is not exceeding the rating of the motor. Okay, because the motor's been designed to handle so much current. Yes, there's a starting current that starts up, but that's only minimal. That runs for a couple of seconds and back down. Once a motor turns on and gets up to full peak, it comes back down. Okay, if that excessive current stays on there for an extended period of time, it puts heat on the windings, and windings start to fall apart, and they can short out between each other. That's what I was talking about, checking your windings, make sure your windings aren't short-circuited. So the current shown on the nameplate is the maximum rated current for the motor. During normal operations, the current drawn should be somewhat less. Okay, so you should always have something less. Overheating. Another cause of overheating is the air passages need to be free of dirt and debris, so the motor's got to allow. So that's why some of the motors are open to allow air in and out. It's got fins on it to blow air to cool itself down. You know, so you have to allow air to move through it to keep the motor. That's what it's designed to handle. You want to make sure it doesn't cause it. Motors that operate in areas where the temperature are usually high must have additional means of cooling. Venting will reduce heat buildup and help the motor dissipate heat. Excessive high cycling. Single phasing. Cause motors to slip or start and direction. So what is single phasing? Single phasing is when you have, let's say it's 12208, and all of a sudden one of the phases drop out. But the motor's still trying to run. It's trying to, there's nothing there to make it turn, but it's just trying to. Guess what? The windings start to get hot. Why? Because it's not moving. A common cause for motor failure occurs when one phase of the three-phase power opens, leaving the motor running on remaining two lines. This causes the motor to slip, which in turn creates heat and vibration. Sometimes single phasing occurs when the motor is not running. When the motor eventually starts up and either start in the wrong direction or simply vibrate and hum. To verify single phasing, use a measure each of the motor's phases to ground. Two values will be correct and one will be significant. So when you're doing that, well, hot to ground, hot to ground, hot to ground, hot to ground, you should get the same voltage. If you have 0 on one, and then there's your problem. Either the fuse is bad or maybe the breaker went bad. Finally got a breaker today. You know, so you got 100. Here's a 2-pole. I got a 3-pole back there somewhere. I just couldn't find it. But I got 2 hots coming out of here. Let's say this breaker, half of the breaker goes bad internally, or the breaker tries to trip, but only half of it trips. Okay, so the motor sits there, and then you got a hot on it, and it just tries, and it can cause excessive heating. Excessive cycling. Okay. So you sit there and you're jogging or you're playing with the buttons. Okay, the motor is just and it doesn't have time to heat, to cool down, or to cool itself down. When motors are started, they draw much greater current than when they're running. Repeated start, jogging, and reversing will not allow the motor a significant time to cool. Heat buildup is certain to occur, causing the motor to burn up after a relatively short service life. So never sit there and play with the motors. excessive moisture. Unless a motor is designed to be placed in a wet environment as a cause of totally enclosed motors, it will not last long in such conditions. Moisture is a form can severely damage open frame motors. Precautions should be taken to protect motors from moisture in any form. Okay, so when we're working for these motors, you have to have a motor. We had one that kept burning up. It burned up after 6 weeks. We ordered a new one, and I told him, boss, and I said, we knit this one. Well, what's there right now? So I told him what was there. And my supervisor went to check to see how much these enclosed motors were. He says, hey, that motor cost blah, 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 10 times more than the open motor. So he just bought the open motor. And we put it in. And sure enough, a month and a half, 2 months later, that went bad. He says, hey, no problem. We only use the machine, maybe once or twice a week. And it's cheaper to just replace that motor to replace it. And I said, well, if you replace the motor, he goes, yeah, well, we can go a year without having to worry about the cost. And I said, well, after a year, that machine is, the motor, you paid one time, that motor's paid for. Guess what? The machine goes down. Today is the day they're going to use that machine. So all of a sudden, that production is stopped until we get another motor. So how much is it? He goes, well, you could do something else. And I said, okay, fine. That was beyond me. You know what? I'm just a worker that put it in. So, but they didn't want to change it. We had another one, same thing. That machine ran 12 hours a day, and the motor, in order to get to that motor, you have to take 3 motors apart. Okay, because of the conveyors, the way they work, you have to sit there and balance everything out. The limit switches and everything else have to be put in order to make sure it was running right. So it can take up to 4 hours to change the motor and get the motor going. I kept telling them, I said, man, just change the motor out. No. That's what came with the factory. That's what we're going to put in. Now, that was beyond me. Somebody else's call. But when the machine's down for 4 hours, production stopped on that. On page 250 and 251, it says motor control troubleshooting chart. So take a look and go through it. I'm not going to cover it. So you can see, read some of the conditions for the contacts, the coils, overload relays, magnetic and mechanical parts, pneumatic timers, limit switches, manual starters when you turn on manually. Okay, these coils can go bad. Okay, this one you can't replace it. So this one you have to change out the whole thing. But the ones I got in school that has the coils, I got one that's square D, and I have another one that's GE, and I can't remember what the other 3 starters are. But I have multiple name brand starters. Okay, each one, the coils are replaceable. Just take it off, throw it out, put another one in. Manual starters is a switch. You got a switch, turn it on and off. So you have here, so you have the causes, contact shattering, poor contact control, low voltage. So it sits and it doesn't close, so the motor doesn't turn on. Welding or freezing. So different things that are on there. So read through them. Noisy magnet, broken shading coil, dirt or dust and magnetic faces, low voltage. So on the contacts, where is it? I'm trying to get to the one with the coil. Oh, here's the magnetic. But these parts, the coil going bad and it doesn't close, or sits there and shattering. The contacts behind get dirty, so they don't make solid contact. Sometimes you got to go in there and clean the contacts off. Why? Every time it makes contact, it makes a spark, so you have debris that build up. So sometimes that debris does not allow it to sit there and close. But sit there like you're clapping your hands. Preventive maintenance. It says preventive maintenance means keeping electrical equipment in good condition so that the operation of the facility can operate with little to no interruption. This keeps problems at a minimum to avoid costly plant shutdowns. Keep equipment in good condition. It reduces downtime. Regular maintenance programs can lengthen service life and minimize potential hazards. As a bare minimum, the following equipment should be regularly inspected. So you should check the transformers, lighting fixtures, cables, switchgear components, circuit breakers, relays, motors, and metering equipment. So check the transformer. If you have an oil-filled transformer, check the levels. Make sure the levels are at. Make sure if it's pressurized. Motors, you got bearings on it. You got to grease the bearings. Why? So you want them to move freely. It says caution: do not use too much lubricant on a motor. Excessive lubricant can leak into the motor windings and cause severe damage. So again, when you're doing things, you have to check certain things. Motors and maintenance specified in manufacturer's manual. So I'm going to end it here. There's a assignment that'll be coming across with this. Hold on, give me a minute here real quick. I got a couple of minutes. Go back. Oops, wrong way. Alright, so the contact shattering. The contact, I'm talking about that. That'll make contact control. Replace the contact, check coil, terminal voltage, make sure your contact, guess what, if your voltage is not good enough on your coil, again, if your transformer is 7.5%, well, guess what the voltage is on these contacts. So if your voltage is too low, they're not close. It's not enough to maintain it closed. Welding or freezing, abnormal inrush of current, rapid jogging, insufficient tip pressure, low voltage preventing magnet from sealing. So it freezes, it's welding in place, or it's freezing. Okay, sometimes your contacts, I've had one that blew up and the contacts stayed in the lock position. There was a fault, and when it closed, those contacts welded on. They just had to, luckily I was there to turn the disconnect off. Short circuit or ground fault. That's just says remove faults and check to make sure fuser breaker is sized correctly. Going back, and that's what happened with that one. Somebody went in and put a breaker in. Somebody wired this motor in, and he put a breaker in, and they had to order a new breaker, so they just tied in to an existing breaker that was already in there. I don't know what happened, or they were just too lazy to change it out, whatever the fact may be. Okay, breaker should have been like a 30 amp breaker, and there was a 70 amp breaker, so they had these number 12s on the 70 amp breaker. You should have seen the wires melted back about 2 inches on all three of them, and the contactor was stuck in the on position, and the breaker didn't trip. This is how we were in there doing some not working on that one, we're working on another one. And when we turn power off and turn power back on and something else, this was about 3 hours later, also we could just hear this noise. Short tips for life: filing or addressing interrupted excessive high currents, excessive jogging. Make sure you don't sit there. Dirt and foreign matter on contact surface. I was talking about cleaning the contacts. These all are on the contacts. Short circuit or ground fault, remove the faults. Loose connection in the power circuits sustains overload. So if you have a wire and you don't tighten the screw down, you just stuck the wire. It's making contact, but it's sitting there arcing because it's making contact, breaking contact, making contact, breaking contact. Why? Because it gets hot and it expands and contracts, expands and contracts. So it causes this arcing. Okay, so loose connection, and it doesn't give you the proper voltage. Noisy mag failure to pick up or seal, no control voltage, low voltage. So if you're magnetic or mechanical parts, okay, make sure your voltage is present. Again, what did it say? 7.5% for your voltage out of your transformer. Coil opener overheating, replace. So wrong coil. I got the one coil, it's 120 volts. I have another coil That's 220 volts. Okay, well, if you put in a 220 volt and 120 volts, guess what? The coil's not going to close because it's not designed for that. The voltage, the magnetic field is not going to be strong enough. Erratic timing, forming matter in the valve. So again, if you've got something that's using pressurized, it can cause problems. Make sure your pressures, if you're using the pressurized controllers, the controls is controlled by, turn it on and off by air pressure or water pressure, something maybe gets stuck in there and doesn't allow it to open and close. Misadjustment or activating screw, worn or broken parts in the snaps, contacts are not open and close. Is pneumatic timers. Adjust instruction for service bulletin, replace snap switch, so your switch may be broken. Replace complete timing head or return timer to factory for repair and adjustment. So it's foreign matter. Failure to drop out gummy systems on pole surfaces, clean pole surfaces. Voltage not removed. So again, you go in there and you hit the stop button and the contact stays on. Well, somewhere along the line something is faulty. So the switch may be stuck, so you have your push buttons. Okay, talking about push buttons. So you got your push buttons. You're on, and you start and you stop. So all of a sudden you're hitting the stop button, and it doesn't close. Well, maybe the stop button went bad and is not making contact. These do go bad. Okay, has little contacts, and those contacts can burn out. Okay, because every time you touch it, it makes that spark when it makes a contact. So they can burn out. Sometimes you have to replace these. Okay, your start button. You hit the start button, nothing happens. Motor doesn't come on. No, you have voltage here first. Then you go to the contactors. Voltage coming to the contactor. Input voltage coming in. This is your controls. Okay, you have different relays along the line. Check your relays. Make sure proper voltage is there. Alright, like I said, I'm sending an assignment with a video, and then we'll finish the book out tomorrow. Alright, y'all have a good night. Stay safe and indoors.